Hello, Eric and Ryan. Hello, how are you today?
Good, bad.
Why? You're good, yeah? Okay, so previously we talked about the list. They
Had nothing to do. We
look,
just
we
went
got
to
talk about list. We have talked about the stack. Yeah?
Whee!
Remember?
Yeah.
And we talk about the queue. Yeah? Yesterday we talked about the set. Remember the set? Yeah?
Yeah.
The Venn graph, okay? Today we're going to talk about the tree.
Tree.
What is a tree?
It's a tree. Oh,
It's a tree. Okay, so tell me, draw what kind of tree you think it is.
I can't really do it with straight.
That's okay. Okay, that's too much details. Okay, tree, what kind of tree is that? Well done. Wow. Okay, that's your
I'm
tree,
not
okay?
done.
Okay.
I'm not done.
Okay. Look, that's the tree in Eric's.
Baby.
Yeah.
Baby.
That's Ryan's kind of
I'm
tree.
never done. Baby.
Okay.
Baby.
Tree doesn't have the fruits, right? Okay. Okay. Yeah, you gotta. Okay. Okay. So the tree,
Whoa.
what kind of what does the tree have?
I think apple. I think the math tree is something like maple tree.
Maple tree?
Like that. Ash tree, willow tree, or like that.
Okay.
I
Okay.
think
Okay. Too many apples. Okay. Ryan, that's good enough. Ryan. Okay. Maybe you should color it later with the apples red. Okay. Yeah, that's okay. Thank you. Okay, sit there, please. Okay, so what do we have for a tree? What does the tree have?
a tree.
Have the root? Yeah, the root. Yeah.
Stem. Leaves.
Stems? Yeah.
Leaves. Apples.
Okay, apples.
Green.
Fruits. Okay, all
It
fruits.
doesn't
Yeah.
have to be the.
But not every tree have these apples or fruits. Yeah. Alright. So we don't.
Oak.
Okay. So now the trunk. Okay. We have a trunk. Yeah. The trunk. Okay.
Yeah.
It's called trunk. Okay. So these are the trees in real life. But in computer, in data structure, we plot a tree. This is the interesting
It's
part.
like a circle, then that.
Yeah, you saw this picture, yeah? Ryan, yeah? It's like that, yeah?
Yeah. Then another circle, then over our side. And
Yeah.
then-
So what you notice is upside down, right? This is root. Yeah? Root. And then these are the leaves. Leaves. Okay? Leaves. Leaf node. Okay?
Yeah.
So it's upside down. So another thing notice is that every node can have only maximum one parent. That's his parent, okay? So if I okay, don't worry about that. Okay, so look.
A.
Let's write this 1, 2, 3, 4, 5, 6, 7. So 2 is 5's parent. Okay? That's his parent and that's his kid. So try and note. Okay? 5 is the kid of 2, 6 is the kid of 3, 6 and 7 are kids of 3. 3 is the parent of both 6 and 7. Okay. So can you tell me which node does not have a parent?
Boo.
There's one node which doesn't have a parent. Which node does not have parent?
What's a parent? A 1.
Yeah, 1 doesn't have a parent. Ryan, can you sit down please? So 1 does not have parent because it's the root. Ryan, okay, come here, Ryan. So look, a tree, so a parent, so one property of tree is that a triad can have at most one parent, yeah? Okay,
Yeah.
okay? And a triad and a parent can have many triads,
Yeah.
right? Children, okay? Okay, so this is called a tree. Now, another property is that if if we say a parent can have at most 2 kids, okay? So if a parent can only have 2 kids, so he cannot have more, right? Like that.
You missed 4.
That's okay. So this, if a note, a parent can have at most 2 kids, we call it binary tree, because you know what's this meaning, binary.
I know library.
I know binary is 2, you know, it means 0 or 1, 2 maximum. Let's call binary tree. Okay, do you get it? So we cannot, if it's binary tree, we can call this left triad, and this is right triad, right? Left, we can call it right, alright?
Yeah.
Alright? Left triad, because it's binary, yeah? This is very important, a binary tree. Okay, so another thing is what? If it's a binary tree, okay? If it's a binary tree. So if it's a binary tree like that.
Binary trees are so terrible.
So that's 1, 2, 3, 4, 5, 6, 7. So if it's a binary tree, and every triad except the last, you know, it's every parent, yeah, have two kids, and except the kid and the leaf nodes doesn't have any child.
He must be the uncle.
Oh yeah. No. Grandparents,
Yeah.
mom and dad. Okay. Yeah. No. Actually, this is a parent, and then have 2 kids. Then we call this a perfect binary tree because it's perfect. You see every. So can you tell me if it's a tree, if a binary tree is perfect, and how many nodes is it? Suppose there are 3. The depths. We call these depths. You know the depths.
Yeah.
Okay.
It was 7.
Yeah, it's 7. How do you know? And how about if the depth is 4? And how many nodes are there?
2.
Can you count? If it's the depth, look. If its depth is 3, if the depth is 3, we got the total nodes is 7. Yeah, it's 1, 2, 3, 4, 5, 6, 7. If its depth is 4, we can have another 2 here, another 2 here, another 2 here, another 2. So how many? How many is there?
15, baby. Oh yeah, baby.
And what's the next if the depth is 5?
That would be 31.
Wow, that was quick. How do you know?
Because I know.
Do you know how to get it?
No.
Suppose the depth is d, and the total nodes will be 2 to the power of d minus 1. Am I right? Look. If d is Ryan, I'm going to put that on YouTube. If you behave bad, people will see. Your friends will see. Okay, so behave well. Okay. Can you come here, please? Anyway, that was well done. Okay. D, if d is 3, look, 2 to the power of 3 minus 1 is 7. 2 to the power of 4 minus 1 is 15. 2 to the power of 5 minus 1 is 31. Okay? Get it?
No.
Yeah?
No.
How do you get it's 31?
Because I know. Because nothing. We know that's 15. So 15. Okay, so that's 8. Double 16. 15, that's 16. 31. Damn.
Okay, 31. Okay, so this is the equation, yeah? If the depth of the binary tree is d, the perfect binary tree is the node has 2 to the power of d minus 1 nodes. Okay? Do you get it?
Yeah.
Like 2 to the power of 2 minus 1 equals 3. Okay? There's 1, 2, 3. Okay? Get it?
Yeah.
Easy. And only one node. 2 to the power of 1 minus 1 equals 1. Yes. It makes sense, yes? Yeah, because we only have one node. It's only one depth. Depth equals 1. Okay? This is called perfect binary tree. Okay? Got it?
No.
You don't get it. Do you want me to tell you again?
No.
Okay, that's okay. You can you sit there, please? Properly, Ryan. You've been good. Okay?
I want to sit there.
Okay, you want to sit there. Okay. Okay, now this binary tree. If it's a perfect binary tree, okay, we're just talking about the perfect binary tree. Perfect binary tree. Perfect binary tree. So how can we store it in the computer?
Def.
No, not the def. We can use the list to store it. So how do we store it? Like that. Look, if it's 1, 2, okay, 1, okay, let's call it. Let's start from 0, okay? That's 0, that's 1, that's 2, I feel tickling, that's 3, that's 4, that's 5, that's 6. So how do we store in computer? We can store in a list. Like that, list. List is the root node. Okay, let's store it 1, 0, 1, 2, 3, 4, 5, 6.
And the 7,
Okay?
8, 9, 10.
So look, the left node, the triangle of
Trial, error.
look, the if the parent two parent 2, and how can I get a parent kid 5?
2 has kid 5.
Yeah, how do we do it?
I don't know.
Look, 2 to the power 2. If it's 2,
To the
its
power
parent,
2.
its kid is 5, 1 5 and 1 6. So this is index. So we can get to the index, right? Look at this 2 times 2 plus 1. That will be its left kid. 2 times 2 plus 2. That will be its right kid. Alright? The second kid. Let's take 1 for example. 1 times 2 plus 1 equals 3, right? And 1 times 2 plus 2 equals 4, okay? So get it? Okay, so let's do another example. 0. 0 times 2 plus 1 equals 1. 0 times 2 plus 2 equals 2. Okay, so does it make sense?
No.
So if it's a perfect binary tree, if the index, we store it in an array, if the index of parent of node is I, then its left kid is 2 times I plus 1, and its right kid is 2 times I plus 2. Am I right? Do you get it? So we can store in a list. Okay? Do you get it? Okay, so how do we visit the let's say, okay, let's give an example, okay? For example, let's given this tree. Can you be good boy, please? Okay, that's the coding part. Okay, that's the coding part. So if a tree is binary, and I want to compute, I want to compute the path. How do I do it? Like if it's a node, is like that. It's 3, 5, 7, 9, 10, 11. Just this one, and the other 7. Okay. Let's give it a tree like that. Let's give it a tree. So if I want to visit the tree I want to visit this order in an order. So if I want to visit this tree by 3 and then 5, 10 and then 7, 9, 11, 7. How do we do it?
3, 5, 10.
How do we do this level by level?
You just wait. Can the 3 be all by itself?
3 what? 3 by what?
All by itself.
No.
You just time.
So that's one example of. Ryan, can you please come there? Is still running?
Yeah,
it's
still running.
Busy. Okay. So this is interesting part. Okay, we can do this. We can have a queue, right? This is a queue. Okay, look. Remember, we have a queue. Alright? We have a queue here. Queue. Remember, first in, first out, right? Okay, so now we are given a node 3. We're given a node 3. We put it here. Okay. Then y q is not empty. We take one element from the q. Yeah, we take it out and push it on its kit. So its kit is 5 and 10. Okay. And I put it 5 and 10 here. Okay. So now 3 is here, right? I put it 3. And now I put another. This q is not empty. I take another element from q, which is what? 5. And its kit is 7 and 9, right?
Yeah.
I put it in a queue. Yeah, at the end, okay? Okay, so now tell me, what's the next item I need to take from the queue?
10.
10, okay, here. And then what's its kit?
11 and 7.
11 and 7.
Why?
Okay, so before it's 10, yeah? Okay. Now 7 doesn't have a kit, I just take it out. 9 doesn't have a kit, I take it now. 11 doesn't have a kit, I take it now. And 7 doesn't have, I take it out, okay? So look, this is the...
2 sevens.
Yeah, because there are 2 7s. So look, this is level by level travel, okay? Do you get it?
There's none of me.
Okay, sorry?
There's no me.
Me, what me?
I'm 8. No 8.
I know, I'm just making it up, okay? So
But
we use a queue to do you get it? Yeah? Every time we push a queue, we put a node here, root here, and then we push his kit into the queue, and then we do it until the queue is empty. Okay? Okay, and I'm going to introduce another tree. Okay? Come here. Right. So this tree, how is that useful? One useful thing. How about if I said this is 7, okay? Tell me what kind of tree you find is this one, okay? And just example, okay?
How do you know 6 and 10 goes with 7? Made it up.
I just made it up.
That means 8 now. Oh, no, 6.
No, let's do it.
8. Yeah. 7. And the ground. 9.
Okay, can you tell me what do you find this tree?
I find that 8, 7, and 3
Yeah.
goes.
Look closely. What do you see this tree? What is it like?
I found out that I'm 6 and go 6 and I go 8 and now it's 8.
Eric, can you find out what is this tree? I mean, what kind of thing is particular about this tree?
What?
I give you a hint. Look at the numbers. Is 6 smaller than 8? 10 is bigger than 8?
The
Okay.
biggest.
So
Small.
you think you get it, okay? Can you tell
Small,
me?
getting bigger, getting bigger, getting bigger, then getting bigger.
So what
Getting
happened on left and
smaller,
right?
Getting bigger.
Huh?
What?
So what happened to the tree? I mean, look, the left are always smaller.
No.
Yeah, can you tell me, please?
It's too much food.
You are very close to it. You are very close to it, Ryan. You want to have a look?
Yeah.
Ryan, you want to have a look? The left node is always smaller than the parent. The right node is always bigger than the parent. Look, 9 is smaller than 10. 11 is bigger. 7 is smaller. 7 is
This way
3
get
is smaller.
smaller,
7
this
is
way
bigger.
get bigger.
Yeah?
Yeah.
So we can call this tree
Food.
binary.
Search.
Yeah, binary search tree. How do you know?
I just heard it before.
Okay. So for a binary search tree, it means that the left nodes always smaller than parents. The right node always bigger than parents. Why is that useful? Because look, if we want to find the number 9, right? Yeah? If it's in an array, we don't know if it's like that. If it's an array list, we have to search If there are n items, we need to search n times to find the 9. Okay, if it's in the last element, right? But for this, we don't. Look, we 9. If it's bigger than 8, is it bigger than 8?
Yeah.
Yeah? So it must be in somewhere here, right? And we don't need to consider this bit, right? Because this bit is the left is always smaller than 8. But I'm looking for 9. So it must be somewhere in the right tree, right?
Yeah.
Okay, and is 9 smaller than 10?
9 smaller than 10.
Yes, then we go left. So every time we go left or right, depending on the value. Do you get it? Yeah? So look, we only need to find 3 times. Compared to this linear search, we are faster, right? Yes? Yes?
Yeah.
Get it?
Yeah.
Good job. Okay, so today there'll be no coding, okay? Because this is a bit difficult. We'll do the coding in the next lesson. Yeah, when we introduce more about the tree. Okay? Happy? Happy?
Nothing happens.
What happened? Nothing happened. Okay, so can you draw a tree? A tree in computer, right? Yes? Come here. Just to make sure you remember this. Can you draw a tree?
A maths one.
Yeah.
Mine takes quite a long time.
Okay.
I have to put some detail to make it more look like a tree. Wait, that.
Well done, you draw a good tree.
Tree.
Okay, that's it. That's good. Okay, that's it.
But I'm not.
So can you tell me? It's okay. I mean, can you tell me? Yeah. So what's this tree? What's this tree?
Binary tree.
Binary tree. Also a perfect binary tree. Yeah. Am I right? Okay, good. No, this is upside down actually. This is the root, and then this is the leaf. Okay?
Yeah.
Okay, good job. Okay, say bye bye to the video.
Bye bye.